but we're just about to get into Unit 9. Let me go back here, sorry. We're just about to start Unit 9. We just finished the unit on some basics of graphing. We talked about all different types of graphs. Now we're going to get into a completely separate unit. This unit is titled Factoring Quadratics. So in this last unit, when we were talking about graphing, we talked about what a quadratic expression looked like. It was one with an x squared in it, or it looked like this little u. That's what a quadratic is. F of x equals x squared. Anything that had an x squared, or this parabola or quadratic shape was a quadratic function or a quadratic expression. So this unit is all about factoring quadratic expressions. And you don't know how to do that yet. You don't need to know how to do that yet. That's what we're going to be talking about in this unit. So we're going to start off pretty basic. We're going to be talking about what factoring is, what a greatest common factor is. We're going to be factoring at a very basic level. So by the end of this lesson, let me move this. Oh, sorry. Let me move this out of the way real quick. By the end of this lesson, this is what I hope that you are able to do. I want you to be able to find the greatest common factor. That's what this GCF stands for. I'll use that to abbreviate sometimes. I want you to find the greatest common factor of a set of several numbers. And I'll also want you to be able to find the greatest common factor of a set of terms in a quadratic expression, and we'll see what that looks like. Okay, so when I say, quote-unquote, greatest common factor, this is what that means. And if you have these guided notes printed off, these notes, my PowerPoints will match up with those notes. If you don't, I would recommend you go back to the home Canvas page and print off these guided notes. If not, please just take notes in a notebook or something like that. But the greatest common factor is the greatest factor that divides into two or more terms. In other words, the largest number that divides into two or more terms. For example, if I gave you the term 4 and 8, and I would want you to find the greatest common factor of those terms, I'm wanting you to find the biggest number that will divide into both of those. So right off the bat, you might be able to tell just straight up what the greatest common factor is. Right here I tell you the greatest common factor of 4 and 8 is 4, because 4 is the largest number that divides into both 4 and 8. So 4 divided by 4 is 1, 4 divided by 4 is 1, 8 divided by 4 is 2. 4 is the largest number that will divide evenly into both of those numbers. There's another method of finding the greatest common factor that might come in handy in the upcoming units. So if you remember a little while ago, we made little factor trees. When we were talking about number prison, simplifying square roots, we made these number trees where we wrote down the factors. So the factors of 4 are 2 and 2. Those are the prime factors. The factors of 8 are 2 and 4, and then here are 2 and 2. What I'm going to do is I'm going to circle all the numbers that are in common in both of these factor trees. So here's a 2 in both factor trees. Here's a 2 in both factor trees. That's it. So notice my greatest common factor is the number I get when I multiply all the prime factors that are in common in both of these numbers. So I had these two 2's in common with these two 2's, so my greatest common factor is 2 times 2, which is 4. So that's how I find a greatest common factor. And that's the biggest number, the largest number that can divide into both 4 and 8. So let's practice this a little bit. Let me move my camera out of the way a little bit. Let's practice finding the greatest common factor. Again, some of these you might not need to follow that method, but I'm going to go on that method at least for this first little bit. So I'm going to write the greatest common, or I'm going to write the factor trees for 6 and 12. So it's going to look something like this. So let's see, I have a 3 in common and I have a 2 in common. That's it. 3 times 2 is 6. So the greatest common factor here is 6. And 6 goes into 6 and 6 goes into 12, so we're good. Let's find the greatest common factor of 9 and 15. So I have 3 and 3 makes 9. 5 and 3 makes 15. I can't break those down anymore. So I have a 3 in common, and that's it. So the greatest common factor of 9 and 15 is 3. And to double check, 9 divided by 3 is 3. 15 divided by 3 is 5. We're good. That's the biggest number that could evenly divide into both of those. Let's do 4, 8, and 10. So 4 is 2 and 2. 8 is 4 and 2, and then 2 and 2. 10 is 5 and 2. So right off the bat, I can see I have a 2 in common. And that's it. That's the only common factor between all of those. So the greatest common factor of these three numbers is 2. 4 divided by 2 is 2. 8 divided by 2 is 4. 10 divided by 2 is 5. So that's how I find the greatest common factor. Here, let me look at 1, 7, and 13. If I were to try to break these down into my prime factors, notice I can't. The only prime factors, the only numbers that multiply to make 1 are 1 and 1, 7 and 1, 13 and 1. Each of these are prime numbers already, so the greatest common factor is 1. It's the only number that will divide evenly into all of those. So what about this situation? If you remember back when we were simplifying square roots, we sometimes had variables. We had x's and y's and n's. So I'm going to write this the same way. I have one n here, I have two n's here, and I have three n's here. I have one n that's in common in all of them, so my greatest common factor is n. Okay. So that's how I find the greatest common factor of a set of terms. So what if I have variables as well as numbers? What if I have numbers and I have some b's and some x's and some y's? Well, I'm going to follow, again, the same pattern with this factor tree as I've done in the past. So for b, that's it. I just have b. If I'm breaking down 10b, first I'm going to break down the prime factors of 10 and get 5 and 2. So I have 5, 2, and b here. Those are all my factors. Notice the only thing in common between these two is the b. So the greatest common factor of these two terms is b. Just b. Let's do this one right here. So if I were to try to break down 3, I can't because 3 is prime, so I just have 3 and x. And if I break down 6, I get 3 and 2. So I have 3, 2, and x. So notice here I have a 3 in common, and I have an x in common. So my greatest common factor is 3x. Both of those multiply together, 3x. And notice if I were to take 3x divided by 3x, I'd get 1. If I were to take 6x divided by 3x, the only thing I have left here is 2. Notice that. That's going to come in handy here in just a minute. Okay, let's try to find the common factors of all of these. 2 is prime. I can't break that down anymore. 4 is 2 times 2. 8 is 4 times 2, which is 4 is 2 times 2. So I have 2 times x times x, 2 times 2 times x, and 2 times 2 times 2. I have a 2 that's in common in all three of these numbers, and that's it. So my greatest common factor is equal to 2. And notice here what I have left. When I took a greatest common factor of 2 out of each of these numbers, if I took each of these and divided by 2, I get x squared plus 2x plus 4. X squared plus 2x plus 4. See that? See that? That's going to come in handy here in the next little bit. X squared plus 2x plus 4. So I want you to multiply. We're going to go way back to first trimester, multiplying polynomials. I want you to multiply these two polynomials together. I'm going to distribute this 2 into all three of these terms. So that's going to be equal to 2x squared plus 4x plus 8. 2 times x squared is 2x squared. 2 times 2x is 4x. 2 times 4 is 8. That right there is a quadratic expression. That is a quadratic expression. We know that because it has an x squared. It's going to look something like this. So I told you this unit is about factoring quadratic expressions. And this is the first step, what we just did. We took a greatest common factor out of each of these terms. We took a 2 out, and we're left with x squared plus 2x plus 4. So this is the very beginning stages of being able to factor a quadratic expression. Okay, we're going to experiment with this a little bit. Let's factor out the greatest common factor in each of these expressions. So I need to first, with each of these terms, I'm going to find their prime factors. So I can break 2 down into just 2 and 1, so I'm going to leave that as 2 times x times x. 10 I can break down 5 times 2, so this is going to be 5 times 2 times x. What is in common in both of these sets? Well, there's a 2 that's in common. There's an x that's in common. So I'm going to write 2x out here. What do I have left? If I were to divide both of these terms by 2x, what do I have left? Well, notice here I have an x left. Here I have a 5 left. So this expression, if I were to factor it, take out a greatest common factor, would be equal to 2x times, in parentheses, x plus 5. You'll notice if I were to multiply these back together, 2x times x is 2x squared, 2x times 5 is 10x. See where we're going with this? Let's do it again. So 12 I'm going to break down into 4 and 3, and then 2 and 2. 3 can't be broken down anymore. 6 I'm going to break down into 3 and 2. So I have 2 times 3 times x, that's my first term. Then I'm going to have a 3 and an x. I'm going to take care of this minus sign in a minute. And then I have a 3 and a 2. So what do I have in common in all of these terms? 3, 3, 3. That's it. So I can take a greatest common factor of 3 out of all of those terms. What do I have left? Well, I have 2 times x, which is 4x squared. That's what I took out of this one. Minus what I have left here is x, plus what I have left here is 2. So I can rewrite 12x squared minus 3x plus 6, take out a greatest common factor, and write it as 3 multiplied by 4x squared minus x plus 2. Okay, let's do it again. 5 is already prime. I can't break that down, so that's going to be 5 times x. 15 I can break down into 5 and 3, so this is going to be 5 times 3 times x. 10 I can break down into 5 times 2, so this is going to be 5 times 2. I can write, let's see what I have in common between all these terms. I have 5's in common, and that's it. So I'm going to rewrite this expression as 5, and then here in this first term I have x squared left. Here in this second term I have 3x left, and I have a minus and a plus, minus 3x. Here I have a 2 left, so plus 2. So that expression is equal to 5 times x squared minus 3x plus 2. And again, you notice if I were to distribute 5, multiply 5 by every term in this parentheses, I would get this expression back again. Okay, one more. I'm going to erase this, so get this down. I'm going to erase this so I have room here. Here I'm going to have x times x times x. Here I'm going to have 2 times x times x. And here I'm going to have 7 times x. Notice 2 and 7 are both prime numbers. I can't break them down anymore. What do I have in common in all three of these terms? X, x, x. So I'm going to take an x and bring it out here. What do I have left in each of these terms? X squared, 2x, and 7. Keeping in mind the original signs that were in my expression, I'm left with x squared minus 2x plus 7. And again, if I were to multiply or distribute x back into all three of these terms, I'd get back this expression that I started with. And that's it. That's what we're starting with. That's how we're starting factoring these quadratic expressions. I'm starting with just the greatest common factor. So remember, the greatest common factor is the greatest number or the greatest term that can divide into a certain set of numbers. So hopefully now you're better equipped to find the greatest common factor of a set of numbers and find the greatest common factor in several terms in a quadratic expression. That's going to be a really nice segue into the next section that we're going to talk about and throughout the rest of this unit as we continue to factor quadratic expressions. So good luck. I hope that was helpful, and I hope that you enjoyed that as much as I did.